Welcome everyone, thanks for being here. My name is Josh Hartman, and my senior project is titled Big Bertha 2, Design, Analysis, and Construction of a New Pump Performance Test Station for MET 315 Lab. To save a little time, I'm not going to go through every specific item right now. You'll see on the left the table of contents basically, and as I go through, the different sections will be highlighted as I go. And they'll be more or less self-explanatory as I go along. Brief history. The original Big Bertha, as it was called, was developed by the late Dr. Walter Kaminsky, my advisor in the program when I was here before. And so I wanted to do this as a tribute to his memory. And unfortunately, the old setup had to be dismantled. It was an important tool in the curriculum for the fluid dynamics course, and when they needed to renovate the original Hogue Technology building, that had to be taken down. Here's the picture of the leftover pile of parts. The old setup, that was quite large. It took up a wall in the old building. It was quite noisy and not very easy to operate. So we wanted a new setup that would be portable, easy to use. So the main objective here was to redesign and rebuild the pump performance test station in order for students to have the hands-on experience in the lab, and then also for me the goal was to use all the tools I'd learned throughout all my schooling, and then to simulate kind of the real world, getting out into the job market, having to solve problems, manage time and budget, and just going through the process from the concept, design, analysis, and testing all the way through to a delivered product. So the first method I used to achieve the goal of a successful project completion was implementing the practices from the Project Management Institute, and they have a book that outlines different things like time management, cost management, and risk management. That's something the program emphasizes now for students to go through the process. And then another method here was to work with the customer to develop requirements. In this case, it was the MET department and Professor Beardsley. And he wanted something easy to use, portable, and modular. That is, it would be capable of interfacing with other devices down the road. And then I'm going to apply principles from fluid dynamics to evaluate the design as well as perform lab experiments. And some additional analyses that were important to me, the first one being safety, because it's going to be operated by students. I didn't want it to blow up or fall on students or anything like that. And then ergonomics is important as well. I wanted it to be easy to use from a sitting position by one person, everything within reach, no overhead stuff or bending and hurting the back. And then the transportation there I mentioned is actually, I just physically moved it around the building just to make sure I could kind of simulate how students might abuse it in the real world. And then some more methods here were my own skills and abilities, being able to weld and machine and do things with plumbing and electronics. I didn't want to have to outsource a bunch of the labor. I wanted the experience of doing it myself. So the first thing to do was some research. I had a pile of parts. I needed to know what they were good for, if I could reuse any of them. Also decided if there were new parts available. Bought something with some fancy gizmo that would be really cool, but unfortunately the cost was a big concern, and those new fancy gizmos tend to be kind of expensive. And probably my biggest concern initially was being able to complete the project in time. I didn't want to design so complicated that I couldn't get it done. I had started late in the school year. After it started, I'd been out of school for quite a while, and so I was a little bit hesitant going into the project. I went through lots of ideas and sketches, many different iterations. I probably would still be coming up with designs today if the customer, Professor Beardsley, hadn't told me to just lock it in. So that's where I say I worked with the customer to finalize the design. Some early pictures here, prototype stage, early renderings, some of my early sketches. Then I went into the SolidWorks software for 3D solid modeling. Hadn't used that program in a while either, but luckily it was easy to use and intuitive, and I was able to pick it up rather quickly. So on to the analysis phase, my biggest struggle was how do I model this system? How do I test it before I can actually build it? So using mathematical equations, mostly fluids equations, figuring out which ones were relevant, which ones would be useful, as well as simplifications to make. And this here shows some original handwork I did in the analysis. Later I moved on into Microsoft Excel to help generate the data more efficiently. A couple of the main concepts from fluids that I used were the ideas of conservation of mass and conservation of energy. Basically, everything going into a system has to come out of the system. Sort of like accounting, pluses and minuses, everything has to balance out. And also, I was curious if anybody had done this before. I didn't want to reinvent the wheel if I didn't have to. The old Big Bertha had a lot of data available from many years of use. However, it was a different configuration, had a larger pump, a different system of piping. So the results from that weren't quite as helpful as I had hoped. Luckily, I was able to get a hold of this Pentair Pool and Spa handbook, and it had a lot of great tables and charts and useful information about pool and spa design, pumps and piping and that sort of thing. And then I finally tried computational fluid dynamics analysis. It's basically using a computer to solve very complicated equations, time-consuming equations. But I was limited by the student edition of this software, SolidWorks. So unfortunately, I wasn't able to give me the results that I was looking for. So with the analysis done, moved on to the construction phase. I had identified which parts in my research I was interested in purchasing, found local vendors to supply those. Unfortunately, I had to work with the central procurement department and found that to be quite a time-consuming process, so I ended up spending a lot of my own money just to speed things along. But in the end, it worked out well, and no major glitches. I was kind of having trouble figuring out where to go. I was kind of stymied, so I decided to build a prototype. Just slap something together, who cares if it worked or not. So I didn't glue anything, just dry fit all the piping together, made a little frame, and just as a starting point. Some other difficulties I had to overcome, one being shop time. Last quarter specifically, there seemed to be a lot of classes going on all the time, and we needed a buddy system in order to work in the shop, and none of the professors wanted to be here at 1 or 2 in the morning to help keep the shop open. And then another difficulty, just my lack of experience. Hadn't been in the shop in a while, a little rusty on running some of the equipment. And then the final one there, due to my own stubbornness probably, this one was my most difficult obstacle to overcome, was seeking help. But through this process I've learned definitely that it's okay to ask for help. Some other design revisions I had to make. My original SolidWorks drawings weren't modeled quite as accurately as they could have been. And as I was starting to cut and glue and fit things together, I ran into some interference issues. But my new motto now, mistakes are opportunities for improvement. I actually had glued something together wrong, and when I had to cut it off and redo it, I actually ended up coming up with a better way to do it. So don't be afraid to make mistakes. And then finally, construction was finished. Well, almost finished. I'm still working on it technically. Definitely took a lot longer than I originally anticipated. Probably a good 2 months longer. Moving on to the testing phase. I threw in a little bit picture here. Roger doing his little jig of happiness on the first test run. Before I get into that, I'll talk about the safety tests I mentioned earlier. students were going to be operating this, so I didn't want anything to tip over or kill anybody or blow up and that sort of stuff. And then that ergonomics test, sitting in a chair, trying to run the knobs. I've done measurements with range of motion. Professor Beardsley provided a handbook that detailed the ergonomics stuff. And the leak test, this was probably the second most important test. And the first time I fired it up, it was like a fountain, water going everywhere. But I was able to get those fixed, luckily. Didn't fry any electronics. And then the lab simulation test. That's the ultimate goal of this project, is for it to be used by students as an experiment. And so I had to follow procedures that I had written up and the detailed operating instructions. Even just moving it from point A to point B had special instructions. And then the final test was, will it accomplish the goal of being a useful learning tool? And yes, I learned a lot from this, so hopefully the students will too. And that brings me to a little video. Just running it here, I inserted an analog flow meter, measures gallons per minute. I'm just adjusting the speed of the motor up and down to affect the flow rate. The motor is controlled by an alternating current variable frequency drive, which is here. I'm adjusting the wave, the output frequency to the motor, and in turn that turns the pump at different speeds, and that causes the flow to change. If at first you don't succeed, get really frustrated. I was having some difficulty with my calculated data and my measured data matching up. You'll see the data here, my calculations and my measured results. The only reason they look good and fit good here is because I had to multiply by a factor of 10. And in the real world, a factor of 10 is the reason why things blow up and people get killed. A little common sense probably would have told me, looking at the numbers, 56 pounds of pressure per square inch up to about 140. If I'd have thought about this 5 horsepower pump, I probably would have realized there's no way it should have been able to put that much pressure into this system. Luckily, it turned out to be a matter of simply just finding a new pressure sensor. And I wish I would have thought of that a month sooner. But overall, it was a successful design and build. It had good ergonomic features. It was safe, sturdy, portable, easy to use. Actually, in the back of the room, I wheeled it up here with the pallet jack. It's a little heavy, that's the only thing, but it's manageable by one person. Was I on time? Was I on budget? No, unfortunately not. It took longer, it cost more, and luckily within reason. And then the lab results, I didn't include the pictures here, but these are the first pump curves. But the new data seems to support the manufacturer's data quite well, and I think it'll be a good learning tool. So to conclude, it worked. The application of the principles of engineering enabled a successful project completion. And some future plans, my original intent was to hook up the frequency drive, the flow meters, and the pressure sensors kind of hidden here, have them working together with sort of a feedback loop, automated control type setup with PLCs and whatnot. Probably that'll end up being a project for electrical engineering students down the road, I imagine. Before I take questions, I need to thank quite a few people. I have another 20 minutes, right? Most of all, Professor Beardsley and Professor Pringle for all their help along the way, their wisdom and guidance. So without them, I certainly could have done it. Allowing me to get back into the program and not have to take a bunch of extra classes. And of course, thanks to all the fellow students. They've been a big help throughout the process and been very welcoming to me getting back into the student world. Also, thanks to my aunt and uncle in the back of the room there for letting me stay with them and putting up with me. And thanks to all my family, parents, grandparents, siblings, aunts and uncles. Thanks to Mr. John Waterbury. He provided that pool and spa handbook to me. And he was also very knowledgeable in pool and spa design and fluids in general, water in general. And extra super double top secret thanks to my wife.